Okay. Good evening. So in today's presentation, I will show you how containers work. It's a topic that I worked a lot in my PhD, and I have also some stuff still going on there. So containers, belongs to something that is commonly called OS virtualization. So that means that resources are isolated in software only, and this is done by the operating system because the operating system manages all the resources. So it's very granular. Basically, each process can have a different level of enforcement, and there's only one operating system. So this is different from what you usually have with virtualization or hardware virtualization. There you have multiple operating systems that are managed. And this also gives you the advantage that you can easily share resources between processes. So you don't have like fixed memory allocations that you assign to a VM or something like that. You can share them as needed. And the same is also for CPU time. So this makes resource utilization often a bit better. So OS virtualization you can find in every general purpose operating system. It started all with something that is called change root in the old Unix operating system. So a change root, you can think of it as a system call that allows you to select a subtree in your file system as the new root. And then the process that performs the change root then only sees those files. This is an important mechanism to secure some processes that was used in many daemons. For example, you can use it in SSH, as well as, for example, if you have the postfix mail server, it will also use this change root to confine processes in their own space where they cannot access any files but the things that are available in the change root. However, there's one problem with that. This mechanism you can easily undo if you're a root user, because then you can just change root back and then you proc out the sandbox. That's why then later other operating system came up with a more advanced mechanism. For example, Jails is one of these that is basically change root on steroids, and it allows you have zones. And but for this talk, I will more focus on Linux containers because they're also the more popular ones across those variants here. So why are they so popular? So Linux has this advantage over other operating systems that the kernel devs have this premise that they don't want to break user space, which means that their system call API is very stable and it doesn't change. So you can, if you have, for example, this is quite popular in companies, if you have a relatively old operating system running on the host, for instance, you still have a Red Hat 6 running that was released in 2010, then you can still get up-to-date software by running a container on it, and you don't have a lot of overhead except for the additional files that you need. And this makes it then really convenient to use, especially with tools like Docker that abstracts the whole container creation away, and also helps you then with isolating software from each other. And you also get features like a rollback. If you have an application and you continuously develop it, you can go back and forth in time. And this also led then to development like Kubernetes, which is a container cluster manager that then allows you, if you have multiple hosts, like 1,000 or so, and you want to deploy your application to these hosts, then you have things like Kubernetes that helps you with that. A bit more about this later. So let me first talk a bit more about the Linux APIs that are below these containers. So there are many APIs, but I want to limit it to the following. So we have namespaces, C groups, And then there's some things to enforce some more access control policies like seccomp and fmr. So what does namespace? What are namespaces? So namespaces basically limit what resources your process can see. I will show you more in a minute what this means and what kind of resources these are. And then you have C groups, and this limits how much of these resources a process can use. And then you have things like seccomp and fmr, and they basically can enforce further hardening, so they can filter system calls, and if there are system calls or system call arguments that are not allowed, then they can stop this system call with an error, or they can kill the process depending on the configuration. So let me first talk about namespaces. So you have certain resources like mounts and network interfaces, and with namespaces you have several, and they can basically if you open up a new namespace, you can limit what this process or what processes in this namespace can see. And this means that every system call that is implemented in Linux needs to be aware of this namespace. So in every process, there's a data structure called ns-proxy. And if you have certain system calls, they need to check for in this data structure what they should return to the process. So if you have namespaces enabled, then when you start the first process on your system, then it will already get some namespace, and then you only can create a new one if you want. But if you don't change anything regarding namespaces, then if you fork off a child, then it will get the namespace that the parents had before. So here a bit about how you use those. So there's if you create a namespace, there are two options. You have Unshare and Clone. So Unshare basically just creates a new namespace, but it doesn't do anything to the process. And Clone, if you remember the process lecture, Clone is basically the one that creates a new process. So when you clone a new process, you can also say create a new namespace along with this. And this is used if you, for example, if you create any container, for example, if you use Docker run, then this will call unshare and create a new namespace. Then if you have an existing namespace and you want to switch to it, for instance, you have a container and you want to execute anything in this container, then you can use the setns system call to enter the container itself. And this is also done if you use Docker exec and you do that on an existing container, then it will execute something in there after applying all the namespaces. And then if you have a process and you want just to check if you're in a namespace or not, then you can check the prog file system. And for your own process, there's this convenient symlink called proc self, and there you can check the ns directory. And you can, these are symlinks in there, and you can call ls-la, and then you can see, okay, these are all the namespaces. You also will this later in the assignment in the test, you will see that this is also used to check if you created your namespace correctly. If you want to get a different or more in-depth introduction to this topic, I can really recommend a manual for this. So if you open up main namespaces, there's document that goes over every namespace that exists and also what implications are and stuff like that. So I think this is the best documentation by far. Let me go a bit more about what different namespaces exist. So there are 8 so far, and they get added every year basically. For instance, the latest one was the time namespace, which allows you to have different times in different containers. So you can have different time zones. Time zones not so much, but you can set different times in different containers. So I just want to give you an introduction to a few of those. So the mount namespace is the oldest namespace. That's why it's sometimes just called NS, like namespace. So this was how everything started. And it allows you to hide mounts from other processes. And this is useful in the change in combination with the change routers call that you've seen before, because then you cannot easily change back because you can just hide other mounts. Then a different one is called the PID namespace. This basically allows you to hide processes. So you can usually in a container, you create a new container namespace, a PID namespace, and then only processes within the namespace are visible. So this also allows containers to have a new init process. So because the first process, PID1, has a special meaning, it has some special semantics that are defined by the kernel. And with if you would have no PID namespaces, then you could only have the host PID1, and you couldn't make your own one. So this is what enables that. And then we have network namespaces, because often you have containers and you want to restrict what network they can access. You maybe don't want to connect them to the internet at all. And with network namespaces, you can provide your own set of network policies, routing tables, firewall rules, whatever. And then, yeah, often if you see, for example, if you have Docker containers running, then you often see something called an for-if interface, and this is basically something you can think of it as a pipe. So you have one for-if and then the interface running inside the container, and then one running outside of the container, and this provides then some virtual Ethernet interface that you can then connect to a bridge, for instance, and then you can route out the internet. Yeah. And then there's also something that's a bit more important for your assignment as well. It's called user namespaces, and this basically allows you to map a range of users from the host to the namespace in a different range. So why is this useful? So for instance, you can use this to implement unprivileged containers. For instance, you can say, okay, I'm now UID 1000 on the host, which is an unprivileged UID. And then you could, within user namespace, you could map this UID to the UID 0 in the user namespace. And this basically allows you to become root, but only within the user namespace. You don't gain a lot of privileges this way. You gain access to some other namespaces, but you cannot really access resources that you couldn't access before. So, and this way you can build software, you can build containers without having root, and this has some security advantages. So this was so far for namespaces. Now I want to talk a bit about C groups. So while namespaces were more like flat, you can create new namespaces, but they are all basically on the same level. C groups are hierarchical, and they are used to restrict how much resources your process can use. So there are also different subsystems for each aspect you want to control. So just to give you a few examples, what you can do with C groups, you can, for example, limit how many CPU schedule slices your process group gets compared to a different one. You can say, okay, this whole C group only is allowed to allocate 1 GB, including page cache and everything. So you can limit the memory and make sure that one container is not able to take out the whole system just by over provisioning the memory. You can also limit things like block IO, and then there's also a lot of other things. For example, there's a freezer C group, and this allows you to freeze a process or a process group. And then I know someone was using that in their window manager to basically freeze all processes or all windows that are not in the focus. So they basically stop working until they're focused again, and to save resources, basically. Just an example what you can do with C groups. Also to give you some perspective. So let's say we have why they're useful and why we cannot just apply limits to processes itself. So let's say we have a Redis container, and it runs the Redis server, which is traditionally a single-threaded application. And because we have a container, it's also running in its own Redis C group. Let's say we have a different container that runs Apache, and Apache has also a web server, is also, let's say one process, But this Apache is configured to spawn a lot of CGI processes. So for each request, it opens up a new process to generate a web page. So now you would have 1001 processes of the Apache web server versus one process of the Redis container. So now if you don't have C groups, you could imagine who gets more CPU in total. So because there's Apache, it has a lot more processes. It would be scheduled a lot more often, and it would be unfair towards the Redis container because it only has like one process. But with C groups, we can make sure that each container gets the same amount of CPU time. And this is also helpful if, for example, you have a fork bomb or something that spawns too many processes, you can contain them then this way and keep the system as a whole more stable. C groups are also useful for process tracking. This is used in Docker, and also if you don't have any containers running in systemd, which is your init supervisor service in most Linux distribution. And you can put basically each service or container in a C group, and the C group then gets inherited by all childs of this service or container. In this way, you can easily list all members of the C group, and you can say, okay, these processes all belong to the service or container, and this makes management then easier. You can also get event notification. You can say, okay, when there's no process left anymore in the C group, then my supervisor gets notified, and then you know, okay, the service is now finally dead. And this is quite useful if you want to reliably stop processes or services if they do some multi-process stuff. For C groups, if you use them, you will notice there are two versions. There's a C group v1 that was around for a long time, but now people want to switch to C group v2. You still have some container engines that are not really ready yet for C group v2, but I think most of them, like Docker, also are. But there's still some edge cases. And yeah, it's the minor difference there is that the new interface basically unifies all the C groups, while the first version had them separate. So CPU C groups were separate from memory C group and so on. You can all access them quite easily. C groups is just like a file system. I will also show in a demo how this looks like. To create a C group, you can just create new directory inside your C group mount point. And if you want to join the process, you can just echo the PID of this process into that. You need usually root for that. And you can also check your own process membership by reading from proc again. It will show this then also in live how this looks like. So lately, okay, now I had C groups, now a bit about security, because we want to contain our processes and only give them the privileges they need to, and to prevent security breakouts out of the container. There's several mechanisms how you can restrict the process in the container, and also make the root user or the privileged user less powerful. So there's some mechanism for that. The most important is probably capabilities. So capabilities basically allow you to take writes away in a more granular way. For example, often you don't need containers to change their IP addresses after they've been set up, so you can drop the cap netadmin capability. And there are also other capabilities. You can say, I want to only be able to change arbitrary files on my file system, the UID and group ID. Then you need cap change own, but you don't need any other capabilities. So just a few examples for that. And then you also have something called seccomp or seccomp eppf. And this is basically like a small filter language, where you can say if you do an open sys, or if you do a change own, and you set also the set UID bit, which usually allows you to install something like sudo or so. So it's something that could become root at some point. You can basically write a seccomp rule that would drop these type of change own calls. And you don't need to drop the change own call in total. You can be very granular what you allow or not. You can also go further than that, and there's some frameworks that allow you to do more complex policies and rules. For instance, AppArmor or SELinux, and they do even more than that. And usually things like Docker, so they come also, if AppArmor is available, they also apply some default policy to your container. So this was everything so far for the APIs that I used in set containers. Now I want to talk a bit more about different implementations and give you a little overview into what the ecosystem looks like. So it all started with, I would say, so-called system container. So it means that you run multiple, it behaves a bit more like a VM. You put all types of services in one container. You have like a full system setup there. The first generation of container engines went in this direction. So for example, when I started with containers, there was LXC around mainly, and then others joined later. And they're still around today and quite useful. For example, if you're an Arch Linux user, you probably used systemd nspawn at some point to enter your installed system from the installer itself and to do some modification. Then there's a different trend. There's so-called application sandboxes, where you basically package also desktop applications, but it's also used for security. For example, if you run Chrome, it runs certain processes that do process data that might cause some troubles with security devices to Chromium itself. They usually run those in a sandbox on its own, and this sandbox then can access almost nothing except for some IPC sockets to communicate with the outside world. And then, also, for example, in high performance computing, they also use something called Singularity so they can distribute their high performance computing software on different machines. Then you have something called, I would say, application container engines. So this includes things like Docker or Podman or Containerd, which is the new, or it's like the thing that's probably gonna survive the longest. This is also quite heavily standardized. So most of them use the same format defined by the OCI, the Open Container Initiative. And this allows you basically, if you have things built by Docker, that you can also open them in Podman or Containerd. So it standardized the whole format. And then on top of these defined images and runtime environments, you also have then also something called a cluster manager if you want to scale out to multiple hosts, because Docker would then only run on one host. And if you have a second host and you want to schedule containers to the machine that has the least amount of work, then you can use something like Kubernetes or Nomad or Docker Swarm. In our lab here, we also use Kubernetes. So if you run a benchmark or if you submit a test or something like that, then there's a Kubernetes one node cluster that basically spawns a GitHub action runner, and then will run your test in that there, and then it spawns a new one for the next test. I can also show you this in a bit. A bit more about this Oci Image Runtime. I think a lot of you already have used Docker in some way or the other. And if you want to build some image there's this thing called Dockerfile, which is the most popular way to build containers. And this, under the hood, makes then heavy use of file systems or block devices that can snapshot. And this is something you can use to save space, because you can share common file system images between each other. To show you an example, so here you have something, a Docker file that would create a Docker image based on a different image that is downloaded, and it's the Ubuntu image. And when you run Docker build, it will run each of these steps. And for each of these steps, it will create a file system snapshot. So if you see the snapshot here, the lowest one is the Ubuntu one. And then on top, you have a bit of application image that gets added. And then some more image data is generated when you run then the make command. And then finally, you just add an entry point for the container. So this would be run if you run the container. And this doesn't add any data to your container layers. And the advantage is that if you rebuild the container, if you, for example, change the application, but you don't change the Ubuntu image, then only a small amount of data is changed, and you don't need to, if you upload then this container image to some other host, you don't need to transfer for everything, you only transfer the layers that have changed. You can also see, I've put the GIST link. I will also publish the PDF as well. And I published the configuration or the Dockerfile that we use for our CI runner, so you can see what is actually installed on the machine. So yeah, as I said, this is all quite standardized. So for example, if you want to use VMs instead of containers, you can just exchange the runtime, have a different containerd running or so, and then it will use a different execution engine to run your stuff. And you can also exchange the build tools. So if you don't like Docker files because you don't like how it's a bit not too unflexible or something like that, you can also use some other tools that work differently. So yeah, this was everything from the presentation parts. Now I want to show you a demo as well. But maybe I can first look if there's any questions or so. Otherwise, yeah, on first you can also ask some questions if you have anything regarding the task itself. So I think I need to change my screen share to desktop. Can you see my terminal? Can you give me feedback on that? Yes, good, great. So I prepared some simple things here. So it's a demo here, just put in the commands. And yeah, for namespaces, if you want to experiment with those, there's this tool called Unshare. And this basically allows you to create new namespaces. So it works like that. Say unshare, and then you have some arguments here. This strace is only for you, so you can see what system call is used, and it just filters for the unshare system call, which has the same name as the tool. So here we just create a user namespace and then fork, and then remap the current user to root. So if you do that, you can see I'm now root, and but this is only here the case. So if I go here and grab for the sleep, I can still see, okay, this is not root, this is running still as my own user. So yeah, you can then just extend this. For example, you can add more namespaces. So you leave the unshare shell again, and then say, you see here all the network interfaces that I have locally. And now if I run the next command, you see, okay, unshare has now more arguments. Is this also big enough? Yeah, I guess so. Unshare has now more arguments, and it also creates a network namespace in addition to the user namespace. If I now run APA, I can see, okay, there's only a loopback device available, nothing else. And even the loopback device is shut down. So there's no network here at all. So this is basically completely isolated network-wise. You can now do other things like PD namespaces, for instance. If I do a PD namespace and I run PS, okay. Okay. It's still proc. So PS still lists all the PIDs on the system, but this is because proc that we have here, this prog here, that lists the processes on the system, is still the old or points to the old prog. So if you open PID namespace, we only have one PID in here, and we are PID 1. So if you leave this, we have different PID. If you go in the namespace again, then the PID namespace gets created, and yeah. But this is we are only PID 1 in this container. So if you do again, if you sleep and then grep for this, we see we are not PID 1 here. We are only PID 1 in the container itself. So PID namespaces, yeah, you can also use this to perform actions that you cannot use do otherwise. So for example, I cannot set my host name, but within the user namespace, I'm allowed to do that. So I can now set my host name to a different one. And if I leave, then I have my old host name again. Yeah, so what you also need for your assignment, you need a mount namespace. And this allows you then to mount stuff. So I can mount here a tempfs, which only exists in memory. I can create this. This is because my mount has some setuid bit. So this doesn't happen on your system. But now I can mount the system, tempfs, and create some files in there. And you will see they only exist in there. So here you can see the mount point. You cannot see the content that I created. And if I close this, then yeah, it will be gone because the mount namespace the mount namespace gets destroyed and all the mounts get unmounted, which includes this tempfs. So this was creating of namespaces. You can also join existing ones. So I, instead of Docker, I use Podman here, which is a different implementation of the thing. Just to show you the overlay FS stuff. Or yeah, you can see root here in the first line. If I grep for ZFS, you can see this is the root file system that contains all the data. I don't use overlay FS. You probably, if you don't have anything special, any special file system, you might have overlay FS on your system. But because I have Podman ZFS the file system, I get this these type of snapshots. And then yeah, we can get a host name. So this is the container host name gets created. And yeah, if you now grep for the sleep again, then we see we can use a tool called nsenter. So nsenter does the system call called setns. So if you filter again for setns and use the right PID here, then we change to the mount namespace of the container, which means we can execute, sorry, the path also reset. So we can do things that you can do in a container. You can also cut the host name, which is now the thing that runs in the container. Oh, okay, I didn't intend to stop this yet. Yeah, also likewise to name unshare, you can also add new parameters. So M stands for mount namespace, N is for network. So if we now add the N flag as well, we also get network. So you see the container network. Well, if you don't have this, then you see the host network. So you can decide, okay, I want to have these namespaces. You can all have them selected individually. Yeah, bit about C groups. So as I said, systemd also uses them. So every application is also in C group. So if you do, if you filter for Firefox, then you can see that this Firefox process exists within my user slice. So every user gets a slice, and this makes sure, okay, that didn't work. So this should make sure, maybe it doesn't. Okay, different command to show you. So you can also read the C group from here. And you can see, okay, I was on the wrong user slice. It's not just a user slice, it also creates a session below that. And then you can see, okay, the Firefox process is in there. And if I have something else in a different session, you can set how much CPU time each session gets. And the same works then for containers as well. Just to show you, I think we can also create a new C group, and it will be empty. So here you would have usually processes, and now we can just add our own shell. So $$ is the current payD in a shell. And if I now attach this here, you can see, this is quite interesting, for instance. So the current shell is this. And then if you fork off, then the other PIDs change every time, because these are basically sub-processes that gets created. So I mean, this is then how C groups work. And last but not least, I show you the infrastructure that we have for our course. So from my laptop, where I'm currently doing the recording, I can remotely connect to the cluster. And here you see basically runners. And this, for example, I can have a look into the runner. And this is running on Kubernetes. So it's a kubectl command that basically attached to the cluster. And then I can get logs from here. I can see, okay, the GitHub runner is running and it's not processing right now any tests. I can also enter this. I can see here, for example, Protocee is available here, but maybe not if you run it via GitHub. That's then all. You can. kubectl has done a lot of commands. You can see on which host it is deployed, and But that's so much for it. I think I can close my presentation here, and if maybe you have some additional questions. Otherwise, we're gonna have the questions done in the next meeting. The presentation, the task is also published already. The deadline for the task we set for 3 weeks. I mean, it's not, I don't think it's harder than the others before, but we're hitting the end of the year. So if you have some more presentations to do, so you have more time. I will also put this in the README itself. If you have done any problems with setting up NICs, I mean, I will show you the task itself, the assignment. So is it harder than memory allocation one in your opinion? No, I don't think so. It's easier, I would say. Writing in memory allocator is a quite hard task. It's on its own. There are a lot of tests. I try to make the README very long. It's a lot of information. And yeah, you can also, okay, we'll also link some more examples there, because you can use, yeah, you can look how other sandboxes work. So I have other code that does similar tasks, and you can have a look how they work. So you can also, yeah, get your, the way you need to use these APIs from there. Okay, I think I can close this recording, and we see us on Thursday.